Hello you beautiful people, it's time again for chemical reaction engineering, so long time no see. Sorry about that, I was a little bit delayed. Today we want to talk about the recycle reactor, but before this maybe we can start with a short repetition. What did we do so far? I think we started with the Euler scheme and a little bit of MATLAB. So I think MATLAB is a tool that we use quite a lot for doing all the Euler scheme simulations. And with the Euler scheme, there we had, for example, this autocatalytic, and we also did the corona simulation. So then I showed you how to do the semi-batch reactor. Semi-batch reactor, and we also had this the continuous feeding to a PFR and a tank in series. Okay, then we started with changing density. So there we introduced this epsilon. So with this epsilon you can say, okay, my volume flow is my volume flow is the initial volume flow times 1 plus epsilon times the conversion. And we also used a lot of the conversion. So X is the emission amount n dot A0 minus n dot A divided by n dot A0. So we used the conversion a lot, and we use this in CSTR and also in the plug flow reactor. In the PFR. Okay, and so today it's a new reactor type. This will be the recycle reactor. And for the future, there we will have a look at adiabatic or polytropic reactions in our different reactor types. So right now it was a little bit boring. So all the time I ask you, okay, which reactor type is the best one? It was always the plug flow reactor performs normally better than the continuously stirred tank reactor. So PFR was always better than the CSTR if you look at it under isothermal conditions. But if we go for adiabatic or polytropic conditions, then we might find that, okay, now sometimes the CSTR is better. And for this, we can also use the recycle reactor. Okay, this maybe as a short repetition. And now let's start with the recycle reactor. So the recycle reactor is basically a plug flow reactor. So you know the plug flow reactor, you have the inlet volume flow, you might have a change in density, then you can say, okay, the volume flow at the outlet is different from the volume flow at the inlet, and you have a conversion of component A. That was in the last lectures was our basis. And what can you do with this? Okay, now you can say, okay, I recycle a part of my outlet from the reactor, I recycle it to the inlet, and then you have a mixture of your reactor outlet and your fresh feed, and this is passed through the recycle reactor. And so if you just say your R is just your recycle ratio, if you say R should be 0, then you have no recycle, then the red line is gone, and you will have a normal plug flow reactor. And if you go for very high ratios of your R, then this will behave like a continuously stirred tank reactor. So now you could ask, why is it useful? So if you remember how a continuously stirred tank reactor is working, so basically you have it's a big tank, and you have a mixer in it. And if you now look at heterogeneous catalytic reactions, so where you have a solid material as a catalyst, then it's really difficult to mix it very well. So if you have solid, it's not that easily. And if you think of a reaction in the gas phase, then your mixture is not that easy. So you can't just put a stirrer in there, or at least it's not common. So normally the CSTR is very good for the liquid phase, but if you go for heterogeneous catalytic reactions in the gas phase, you will almost find only plug flow reactors. And so here with this you can find a very simple layout how you can transform your plug flow reactor into something like a continuously stirred tank reactor. And so of course in reality you won't go for the recycle ratio up to infinity, but you can find a solution somewhere in between. Okay, and now we want to have a look at the recycle reactor. What do we need? So again, some repetition. I just want to show you how the reactor sizing is done for the CSTR and the PFR. Again, for changing density and constant density, I just want to show you the graphical interpretation. And yes, then I will have a short comment on the reactor sizing for a plug flow reactor. If your conversion at the beginning, so XA0 is the conversion of your component A at the inlet. If this is not 0, so we will need it afterwards, and then we go for a mole balance and a concentration balance for the recycle reactor. To show you some examples, I chose a first order reaction, so very simple. This is just the reaction rate is K times the concentration, and I decided to have a constant volume reaction, and this time it's a reaction where your density is decreasing, so you have a negative sign of your epsilon. And of course I will give you a worksheet so you can practice it at home, and you can upload the results to the email room. Okay, let's start with reactor sizing. This should basically be just a repetition. Okay, I think what you all know is from worksheet 3, there we had that your residence time is, so the residence time is the reactor volume divided by the volume flow at the inlet, is just your concentration difference between inlet and outlet, and you have to divide this by the reaction rate. Okay, and here for this example, if you want to replot this on your own, I used a rate constant of 0.02. The starting concentration was 1 kilomole per cubic meter, so this is the value here, and Ca is the value here. So this is Ca, this is Ca0. Okay, and your residence time that you need for this, just you have to go to Ra. So this is the reaction rate at the outlet of your reactor, and you have to multiply it by the difference in concentration, and then you will find that your residence time should be something like this. Okay, if you want to calculate it, hopefully this works out. This is just the change in concentration, 0.8 kilomoles per, and then so this is 1 over R then okay, and I have to write it here, times 250, and it's minutes over minutes cubic meters kilomoles. So kilomole cancels out, cubic meters cancels out, and you are left with a minute, which is quite good. And this should be something like 200 minutes. Let me check. Yes. So it's 200 minutes. The other option that I also showed you in worksheet 3 is that you can go for a plot where you have 1 over r again on the y-axis, but on the x-axis you have the conversion. And so you start your reaction with a conversion of 0, and if you calculate it, you will find that your conversion at the outlet should be 80%. K stays the same, and here, so it's the same again. You just go here and you can find here your residence time that you need. If you put in the values, then it's your starting concentration is 1 kilomole per cubic meters, then your XA was 80%, so 0.8, times your reaction rate, 250, minutes, cubic meters, kilomole, and then again you end up with a residence time that you need here of 200 minutes. Okay, let's have a look what happens if you have a change in density, if your epsilon is not 0. So here it's a negative value, and you can see, okay, your volume is decreasing. This means your concentration will become higher than compared to the constant density reaction. So this means your reaction is a little bit faster, and if your reaction is faster, this means your 1 over r curve is a little bit flatter. So if you compare it here, it's at a conversion rate of 80%, it's 250, and if you go here for a conversion of 80%, it's 150. Okay, so you have to do the same. If you want to know how big should be your reactor, then it's the conversion times your start concentration divided by the reaction rate. So now you can find here, for this reaction, your residence time is 1 kilomole per cubic meters times 80% conversion. And now your reaction rate, or 1 over the reaction rate, is 150 minutes cubic meters per kilomole. And then you have 120 minutes. Okay, now let's go for the plug flow reactor. For the plug flow reactor, I showed you in worksheet 4, I showed you this equation here. So your residence time you can calculate like this. I just showed you the diagram with the conversion. So it's the integral 1 over r dxr. So you have to integrate on the x-axis. You have to integrate here, starting from 0 till your outlet conversion, and now you have to solve for the integral so for the plug flow reactor, this would be this area here, this is equal to the residence time divided by the inlet concentration, Ca0. Okay, and now I think it's quite obvious what you should do if you have the epsilon not equal to 0. If you have a change in density, then you do the same. You go from your inlet conversion to your outlet conversion, and so this is your area, and the area here equals tau over the inlet concentration. This is equal to this area here. Okay, and the next thing we need to know is the reactor sizing for a plug flow reactor, where the conversion is at the inlet is not equal to 0. Okay, how can you figure out what this means? So let's consider a plug flow reactor here with no recycle. So we are just doing some mental experiment. You say, okay, you have the volume flow at the inlet, you have the mole flow at the inlet, and you have the mole flow at the outlet and the conversion. And now let's cut this reactor in 2 pieces. So let's just split it up. Okay, what does it mean? This means your volume flow at the inlet stays the same. You have half the volume here. You have a mole flow that is something called it int for intermediate or intermittent or whatever, and you have a conversion rate that looks like this. And yes, then this enters to the second half of the reactor, and at the outlet nothing should change. You have your volume flow and your conversion rate here at the outlet. Okay, let's have a look at our 1 over Rx diagram. Okay, so we know the whole reactor, should look like this. Okay, and now we cut it into 2 pieces, so the volume should be nearly the same. This means maybe it's somewhere like here. And what shall we do now? Okay, if we just cut it into 2, then we can say, okay, this would be here my first reactor, so this would be tau 1 over Ca0, and then again I can say, okay, this would be just something like tau 2 over Ca0. Okay. But if we want to rewrite it, we can just say, okay, remember that your volume flow at the inlet times the concentration at the inlet is the same as your mole flow of component A at the inlet. So, and if you just move your inlet concentration to the other side, then you end up with the equation that looks, let's put it the other way around. If you move your volume flow to this side, then you end up with something like your volume that you need is your mole flow at the inlet times this integral here, 1 over Ra dxa. So, and this would be the solution for the red one. So if you want to know this volume here, then you can just calculate it by by your mole flow at the inlet, and then you have to solve this integral. Okay, but what does it mean for your volume 2? So for your volume 2, it's nearly the same. This would just be your mole flow at the inlet, and now you have to do the integration from XA intermediate. So this would be this value here, XA int, up to your outlet, integration XA 1 over R dXA. And sorry about the confusion, I forgot here to write internal. So you stop at your for your volume 1, you stop here with the integration only up to XA intermediate. Okay. So what does it mean? If you split up your reactor like this, then you can say, okay, the volume that I need for my first half of the reactor is just this integral, and for the second part of your reactor, this is this integral here. So this is the initial volume, the inlet volume, and then you have to make sure that you integrate only from the conversion at the inlet here up to the outlet conversion. And what does it help us? Okay, if you have a mole flow, so if you want to calculate the mole flow at this position here, then it's your initial inlet mole flow times 1 minus the conversion. If such a mole flow is entering the reactor and you want to achieve a conversion of XA, total conversion of XA, then you can just use this equation here to calculate your volume for such a reactor. So this means if you're not starting with the initial concentration or initial conversion of 0, but you have already somehow a conversion at the inlet, then this is the equation how you can solve it. Okay, then the next video will be about the mole balance and the concentration balance. To make the videos not too long, I will stop here and start a new video. Okay, thank you for watching, and yes, bye.